Hello guys, welcome again. Today we will be starting our new chapter, which is aromaticity. So before knowing about the aromaticity, we need to know what is aromatic and what is aromatic compounds. So to identify whether a organic compound is aromatic or non-aromatic or anti-aromatic, we check the following order. So we check if the molecule is cyclic to be aromatic, or it should be planar, or it should be conjugation is present in between the molecules, and sp3 carbon atom must not be present, and the molecule must follow Huckel rule to be aromatic. And if one of these point is absent, then it is non-aromatic. Let's see some example. So here is an example. As you can see here in this example, 1 2 3 pi bond are present. So the number of it is a cyclic compound. As we can see, it is planar also. It has conjugation. As we can see, the conjugation is present, and one sp3 carbon is not present. So here one sp3 carbon is present, so it is non-aromatic. And in this molecule, 2 pi electron are present, and due to this positive charge it can form different molecules, so it is aromatic in nature. So it is aromatic. How can we decide this is aromatic? So it is also cyclic, it is planar, and conjugation is present due to its positive charge, and an sp3 carbon is not present, and it is also following Huckel rule. How is it following Huckel rule? As we can see, 4n plus 2 pi electron. So if we put the value of n 0 here, then the value will be 4 into 0 is throughout is 0 pi electron. So 2 pi electron is also aromatic. And in this molecule, as we can see, it is also aromatic in nature. 2 pi electron and 2 positive charge are present, so conjugation can be possible here. So it is also an aromatic compound. 2 pi electrons. There is a very easy trick to remember with what is aromatic or what is non-aromatic or anti-aromatic. So if any of the following point is absent, then it is non-aromatic. And to identify what is aromatic or anti-aromatic, we go from the 2 4 8 2 4 6 8 10 12 14 18. So all these molecules which come in the this direction are aromatic in nature. So all these 2 pi electron, 6 pi electron, or 10 pi electron, or 14 pi electron are aromatic in nature. And if we discuss 4 pi electron, 8 pi electron, 12 pi electron, and 18 pi electron, these are called anti-aromatic. So these are following 4n pi electron in Huckel rule. So these are not following Huckel rule, but plus 2 is not present here, so it is following 4n pi electron rule. So there are some example for anti-aromatic. As we can see, some example of anti-aromatic compound are just like this. This has 2 pi electron, 4 pi electron, so it is an anti-aromatic compound. Some of the examples such as this has also negative positive charge, so this negative charge is counted as 2 pi electron, and this pi bond is calculated as 2 pi electron, so the total will be 4 pi electrons. It is also anti-aromatic in nature. And this type of molecule, just like boron, this type of, it has empty orbital, empty p orbital, so it is also conjugation is present here, so it is also 4 pi electron, and it is also anti-aromatic. Some example which is miscellaneous, as we can see, just like if this type of ring are present, and if we put pi bonds in the molecule, so it has 2, 4, 8, 10, 12 pi electron. So according to this rule, 2, 4, 6, 8, 10, 12, 40, 18, this is table of 2. So if it is 12 pi electrons, so it should be anti-aromatic, but it is not. Why? Because this hydrogen which is present here are repelling each other, so repulsion will be there, and it will go out of the plane, so not in plane. So it is not anti-aromatic, it is non-aromatic, it is not even aromatic. Okay, so these are some example which is miscellaneous. Here are some of the example of homoaromatic compound. So what is a homoaromatic compound? So some because of the so what is homoaromatic? It is like aromatic के जैसे दिखने वाले compounds. So some examples are, so as we can see, this is the example of homoaromaticity. So according to the previous rule, as we have counted, it has 2, 4, 8 and a positive charge. So and one sp3 carbon is present. So according to this rule, it has to be non-aromatic because sp3 carbon is present. But what will happen here in this molecule is this sp3 carbon will go out of the plane. So this is not in the plane, this carbon will go out of the plane, and this molecule will form aromatic like structure. So 6 pi electron, and this is also 6 pi electron, but here sp3 carbon is present, so this will go out of the plane and this will form an homoaromatic compound. Homoaromatic compound, not an aromatic or anti-aromatic. This is homoaromatic compound. This is an example of homoaromaticity. Now let's discuss about some important topic, which is dipole moment. Dipole moment. So what's a dipole moment? It is a polarity or the electron density. It is the transfer of electron density from one molecule to another, or the or where the electron density will lies. It is also represented by charge separation. So the major concept which will happen in this here, let's take an example of this molecule, and let's take another example of this molecule. As we can see, these are some molecule, so we need to know this is which molecule is stable. So as we can see, this has partial negative charge and partial positive charge. This has partial negative charge and partial positive charge. So what will happen after the charge separation is put into action? Oxygen will get a negative charge and this has positive charge. So and in this molecule it has negative charge and this has positive charge. So this molecule will become 4 pi electron system, 4 pi electron system, and this will become 2 pi electron system. So this is aromatic in nature. So this is aromatic and more preferred here, and this is anti-aromatic. So it is not very stable carbocation which is forming after the dipole moment is placed. So this is not major, this will be major. So if the molecule is more stable which is formed, the dipole moment has been more here, so it has more dipole moment. Dipole moment will be more in this molecule as compared to this molecule. So here bond will break when both rings are forming aromatic. How we can see this is, as we can see here no dipole moment has been present. Why? Because if we go from here to here, then this will get negative, this will get positive. So it is also not forming aromatic, this is anti-aromatic, and this is also anti-aromatic, so no dipole moment can be placed here. And in this is also the same, when this will go here it will get negative charge, this will go positive charge, so it is anti-aromatic and this is aromatic, so it is also not possible to put dipole moment here. In this ring, if we go from here to here, then 2 2 2, and one negative charge will form here, so 2. So 8 electron will be present and 4, so this is not possible, but here we have to put this direction, then positive charge will come here and negative charge will come there, so both are the 6 pi electrons. So this is dipole moment is present here in upward direction. And in this molecule it is also aromatic. Why? Because if we put this type of dipole moment, so this will also become aromatic, and this is also become aromatic, 6 pi electron and 2 pi electron. So this is also aromatic dipole moment present here. So these two do not have dipole moment, A and B, and C and D will have dipole moment. So now let's discuss the next topic, which is annihilation effect. So what is annihilation effect? It is the tendency of the aromatic ring, in which, as we can see, if a aromatic ring is present and 2 aromatic ring is present and 3 aromatic ring is present, so according to the conjugation, it has more conjugation and these are also more conjugation, so it has to be more stable, but this is not happening. The stability will decrease and the aromaticity per ring has been reduced, so ring becomes shellfish. So aromaticity, if we go here to here, aromaticity will decrease, the benzene ring will become more shellfish and do not share its electron density, so it is more stable and this is least stable.